Kia ora, Robert McLaughlin here. Welcome to Lecture 2 of Week 10, where we continue our study of nonlinear systems. Last time we looked at fixed points and gave the definition of how they could be stable or unstable. And I gave some examples of one-dimensional systems, and now we'll look at two-dimensional systems, which of course will be a little bit more complicated. So a two-dimensional planar autonomous system, dx dt equals f of x and y, dy dt equals g of x and y. What can I do with this to get an idea about the phase portrait without actually solving those differential equations, which may not be possible? So one thing you can do is sketch the direction field, just as we've done before. We did it for a single differential equation before, but you can also do it when your phase spaces are 2. And the idea is that if the solution curve happens to pass through some particular point, xy, then dx dt must be f and dy dt must be g, which means I can attach a little vector to that point, and that's the vector f of x and y, g of x and y. And likewise, at any different point, I can substitute the values of x and y and get little vectors. So the direction field of a planar autonomous system like that is a little arrow or a little direction attached to each point in the plane. And if I draw enough of those arrows, I can get a good idea what the phase portrait will look like. For example, in this case, I can guess that there will be a trajectory, a solution that looks like that. Over here, there might be one that looks like that. Again, this is better done in MATLAB than drawing it by hand. It's going to be pretty messy doing it by hand. So that's one idea, draw the direction field. The second idea is called looking at the Nullclines. So remember, I'm working with dx dt equals f of x and y, and dy dt equals g of x and y. The curve f of x and y equals 0, because it's called a nullcline, because on that curve dx dt is 0, which means your solution curve must have a vertical tangent. You must be moving either up or down. G of x and y equals 0 is another curve, also called a nullcline, and on that curve dy dt is 0, which means I must be moving horizontally. So if you sketch those two curves, you'll divide the plane into regions where dx dt is either positive, negative, or 0, meaning you're either moving left, right, or neither. Similarly, where dy dt is positive, negative, or 0, moving up, down, or neither. And their intersection, where f of x and y is equal to 0 and g of x and y is equal to 0, well, look at the differential equation on the left. If f is 0 and g is 0, you must be at a fixed point. So for example, if one of these curves looked like this would be the curve f of x and y equal to 0. It could be that f is positive over here. That means dx dt is positive. On this curve, dx dt is 0, which means I'm going vertically. Here I must, and above this line, dx dt is positive, which means I'm moving to the right. Below this line, I'm moving to the left. Let's do this, explore this in an example. Here it is here. And I'm actually going to make a restriction so that x and y are both greater than or equal to 0. Let's find the fixed points. See, the right-hand sides there are quadratic functions of x and y, so there may be several fixed points. Well, from x dot equals 0, I see that either x equals 0 or x minus 8 minus 4x minus y is 0. Well, if x equals 0, then the first equation is satisfied. I substitute that into the second one, and I get either y equals 0 or y equals 3. Or from the second equation, if y equals 0, substitute y equals 0, which sets the second right-hand side to 0, plug that into the first equation, either x equals 0 or y equals, or x is equal to 2. Now there's one other possibility, which is 4x plus y equal to 0 and 3x plus y is equal to 3. Subtract those equations. Oops. Let's just correct that. 4x plus y is equal to 8. 3x plus y is equal to 3. That looks better. Subtract the equations, you get x equals 5. Substitute x equals 5, you get y equals negative 12. But I'm going to rule that one out because I'm only interested in this case in the space where x and y are greater than or equal to 0. So altogether, I get 3 fixed points, 0, 0, x equals 0, y equals 3, and x equals 2, y equals 0 in the first quadrant. So let's draw those to start with. There's 0, 0, 2, 0, and 0, 3. Now the question is, what happens close to those fixed points? Are they stable or unstable? I'm going to draw the nullclines. Here we go. Actually, I'll just okay, so the nullcline, well, there's dxdt is 0 when either x equals 0 and when y is equal to 8 minus 4x. That's a straight line. That's my fixed points. Well, on the first curve there, x equals 0. If x equals 0, then dxdt equals 0, so I stay on the line x equals 0. I stay on the y-axis. Looking at the sign of the second equation, when x equals 0, I see that dy dt is positive when y is less than 3 and negative when y is greater than 3. So that's sort of like an embedded one-dimensional system. The other nullcline is y equals 8 minus 4x, which is a straight line that looks a bit like that. On that line, orbits will be vertical because dxdt is 0. To the right of that line, dxdt will be negative, meaning I'll be moving left, and to the left of that line, dxdt will be positive, meaning I'm moving to the right. I can also do the nullclines for the second equation, which are y equals 0 and y equals 3 minus 3x. Y equals 0. Well, if y is 0, then dy dt is 0, and I stay on the x-axis. I see that dxdt is then equal to x times 8 minus 4x, so that will be positive between 0 and 2 and negative when x is greater than 2. Y equals 3 minus 3x. That looks like this. It's another straight line. On that line, dy dt is 0, so the flow lines are horizontal. Below that line, dy dt is positive. And above that line, dy dt is negative. So now, without drawing all of the other arrows, now I know in which direction I'm going. to the right of both lines, dx dt and dy dt are negative, which means I must be going down and to the left. Between the two lines, I'm moving to the right and down. And to the left of both lines, I'm moving to the right and up. So that's already enough information to sketch in what the solutions look like. For example, I see there must be solutions that look a bit like this. Horizontal there, to down and to the right, down, 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 and now heading for that fixed point. Over here, down and to the left, vertically down. No, I didn't draw that quite right. Let's try again. Down and to the left, vertically down, tending to that fixed point. So from this admittedly extremely messy sketch of the phase portrait, but not using very much information or computer technology, I can see that the these two blue fixed points are going to be, let's see, what are they going to be? This one is going to be asymptotically stable. All solutions that start nearby tend towards that fixed point. This one is going to be unstable. There are some solutions nearby that tend to back towards y equals 3, but there's others that move away and tend to number 2. And this one down here that I didn't draw before will be unstable. Also, all solutions that start nearby move away. So if you look in the printed version of the notes, you'll see a better diagram than I'm able to draw here by hand. So that is one idea. Drawing the direction field with the arrows, or getting a sense of which direction the arrows are pointing in from the nullclines. But the other idea is to use the derivative of the right-hand side of the differential equation near the fixed point, which can give us more precise information, essentially using calculus. Now I'm going to have to do Taylor expansions in two variables. So suppose I've got a fixed point, x hat, y hat, so that f and g are both equal to 0 there. And I want to look at what happens if I start near that point. So I'm going to introduce two new variables, u, which will be x minus x hat, and v, which will be y minus y hat. And I want to look at whether the u and v are going to grow or decay. Well, du dt will be dx dt minus dx hat dt, but dx hat dt is 0. So that is f of x and y. Well, that is, in terms of the u variables, that is x hat plus u, y hat plus v. And now I'm going to expand in the Taylor series, where u and v are small. So this will give me f of x hat, y hat, plus u times df dx, evaluated at x hat, y hat, plus v times df dy, evaluated at x hat, y hat. Those are the linear terms, first derivative terms, plus all the higher derivative terms, but they will all have u squared, v squared, or uv in front. So I just write plus higher order terms, because there I'm going to neglect them. So they will look like u squared, uv, and v squared, and so on. Now the first term is going to be 0, because f of x hat and y hat is 0. When I do the same thing for the v equation, dv dt will equal dy dt. That will equal g of x and y. That will be g of x hat plus u, y hat plus v. Expand in Taylor series. It's very similar. Plus u dg dx, evaluated at the fixed point, plus v times dg dy, plus dot 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 the higher order terms. again, this first term is going to be 0. So in this approximation, in which I ignore the higher order terms, I get a linear system. So what I get is called the linearization. Or you could call it the linear approximation of the differential equation at the fixed point. Let's write it out again. du dt is equal to df dx times u plus df dy times v. Now here these derivatives are evaluated at x hat, y hat, but I won't write those arguments in here. And dv dt is equal to dg dx, those are partial derivatives, plus dg dy times v. Starting to look a little bit simpler. And if I bundle those together into a vector, let's call vector u, I get d vector u dt is equal to a matrix df dx, df dy, dg dx, dg dy times uv, which is just vector u, or du dt is equal to a u. And that is a constant coefficient linear system, which I know how to solve. So there's an easy part and a hard part here. The relatively easy part is to calculate the partial derivatives of the right-hand side. Evaluate those at the fixed point. You'll get a 2 by 2 matrix with some constants in there. This is called the Jacobian derivative matrix. Of the vector field fg, evaluated at x hat, y hat. This is the linearization, and it gives me a constant coefficient linear system. So the easy part is finding the partial derivatives, substituting x hat, y hat, forming the constant coefficient linear system. Even solving it is easy because you just have to find the eigenvalues and eigenvectors. But there is one important qualification, which is that to get this linear approximation, I had to ignore the higher order terms. Now, even though they're very small, there is a question about whether their influence could build up as time goes on. So we'll need to think about that a bit later on. So this has been a rather long, complicated lecture with several new ideas, and we've run out of time now to do an example of this, an example of calculating the linearization, but we'll get on to that next time. So I'll see you then.